Okay, let's unpack this. I want you to picture something for me. You're sitting at a table. Maybe it's a heavy oak library table, or, maybe just your kitchen counter. It's quiet. You've got a blank sheet of paper in front of you with a simple line drawing of a map of Australia. The one of the big distinct chunks. Western Australia, Northern Territory, Queensland, down to New South Wales, Victoria, South Australia, right in the middle, and little Tasmania floating off the bottom.
It sounds peaceful, almost meditative, actually.
It does, right. And next to this map, you have a box of crayons. But, and here's the catch, you only have 3 crayons left in the box: red, green, and
A
blue.
minimalist palette. I like it.
Exactly. Now, your job, the mission, if you choose to accept it, is to color in the map. But there is a rule, a strict one. You have to color the map so that no 2 neighboring regions have the same color. So if Western Australia is red, the Northern Territory right next to it absolutely cannot be red. It has to be green or blue. Simple enough. It sounds like the kind of puzzle you'd find on a placemat at a diner to keep kids busy while they're waiting for pancakes.
It feels that way. It totally does. It feels like a trivial way to pass the time. But what if I told you that this little coloring book exercise is actually the fundamental blueprint for some of the most complex systems running our world? What if I told you this specific logic is how we schedule the Hubble Space Telescope to photograph distant galaxies, or how a massive factory organizes its assembly line to build cars without crashing robots into each other, or even how your computer solves a Sudoku puzzle in like a fraction of a second?
It is quite a leap, isn't it? From crayons to the cosmos. But you are absolutely right. That underlying logic, that structure is identical. We are taking a deep dive today into a concept in artificial intelligence called the constraint satisfaction problem, or CSP for short. And this is a bit of a shift for us, right? Because in previous deep dives, when we talked about AI searching for answers, like a GPS finding the fastest route to the airport, we treated the state of the world in a very specific and, I guess, somewhat limited way.
We did. We treated it as a black box.
Explain that. What do we mean by black box in this context?
Well, think about a standard search algorithm like the one that beats you at chess or finds a path through a maze. To that algorithm, a state, say a specific position on the chessboard, it's just a dot. It's atomic. It's indivisible. The algorithm looks at this dot and it asks a really simple binary question. Am I at the goal? Yes or no? If the answer is no, it just moves to the next dot. It doesn't really look inside the dot to see why it isn't the goal. It just knows, nope, this isn't it.
So it's like trying to pick a lock by just smashing different keys into it one after another. You don't know why a key doesn't fit. Maybe it's too long. Maybe the grooves are wrong. You just know it didn't open the door, so you chuck it and grab the next one.
Precisely. It's brute force masked as exploration. But today we are cracking open that black box. We are using what computer scientists call a factored representation.
Factored representation. Okay, that sounds a bit technical, but I'm guessing it just means we are breaking the state down into its internal parts. We are looking at the gears inside.
Exactly. That's all it is. We're decomposing the state into variables and values. And when you do that, when you understand the internal structure of a problem, you gain the ability to solve things that are exponentially more complex than what a standard search could ever touch.
So instead of just guessing, we're basically giving the AI a set of cheat codes. Instead of stumbling around in the dark, it can use logic to prune away millions of wrong answers before it even tries them.
That is the mission today, to understand the machinery of logic that allows us to solve the impossible. Because it turns out the hardest problems in the world aren't solved by guessing faster, they're solved by understanding constraints.
So let's get into the nuts and bolts. If we are cracking open this black box, what do we find inside? You mentioned factored representation. So what are the factors?
In the world of constraint satisfaction problems, every single problem, whether it's map coloring, scheduling a hospital, or, cryptarithmetic, it's defined by 3 letters: X, D, and C.
X, D, and C. It sounds like a government agency or maybe a 90s rap group. Let's break those down. What is X?
X stands for variables. These are things we need to determine, the empty buckets we need to fill. So if we go back to your map of Australia, the variables are the regions themselves. Western Australia is a variable, Tasmania is a variable, South Australia is a variable.
Okay, so X is the what? What are we deciding?
Right. Then you have D, which stands for domains. The domain is simply the menu of options available for each variable. In the map example, your domain is just red, green, blue.
Got it. The what is the region, the options are the colors, simple enough. What's C?
And finally, the most important part, C, the constraints. These are the rules that limit which combinations are allowed. A constraint specifies the scope, meaning which variables are talking to each other, and what values they can take. So South Australia cannot have the same color as Western Australia is a constraint.
So X is the variables, D is the options, and C is the rules. X, D, C.
That's the holy trinity of CSPs. And the beauty is, once you formalize a problem this way, you can visualize it. We call it a constraint graph.
I love a good visualization. Describe it for me. What does that look like?
Imagine a whiteboard. You draw circles for the variables, a circle for Western Australia, a circle for Northern Territory. These are your nodes. Then you draw lines connecting them if they share a constraint. In the map case, you draw a line between them if they share a physical border.
So Tasmania, which is just hanging out at the bottom.
Tasmania is a floating circle. It has no lines connecting it to the mainland because it doesn't share a border. It's untethered.
And this visualization, it actually helps the computer? Or is this just for us humans to feel better?
Oh, it helps the computer immensely. It reveals the structure. Think about this. If you were just guessing, randomly picking a color for every state without thinking, and you had, say, 5 neighbors to color and 3 colors each, in a standard black box search, the computer sees that as 3 to the power of 5 combinations. That's 243 different states to check.
243? That's a lot of coloring, but I guess it's manageable.
For a map, yes. But if you add just a few more variables, that number explodes into the billions. But if you use the constraints, if you look at the graph and say, okay, I made Western Australia blue, and there is a line connecting it to the Northern Territory, so the Northern Territory cannot be blue, that's called constraint propagation.
You're cutting off options.
You are. By enforcing that simple rule locally, you reduce those legal combinations from 243 down to just 32. That is an 87% reduction in the work just by looking at the rules.
That is huge. And that's just a simple map. I imagine for big problems like scheduling thousands of factory tasks, that efficiency isn't just nice, it's absolutely necessary.
It makes the difference between solving a problem in a second and solving it in a million years, literally. And there's another key concept here that makes CSPs special, something that standard search algorithms often struggle with. It's called commutativity.
Commutativity. Okay, I'm dusting off the high school math brain here. That usually means A plus B is the same as B plus A. The order doesn't matter.
Spot on. In the context of CSPs, it means the order in which we choose to assign the variables doesn't matter.
Walk me through that. How does that apply here?
If you are coloring the map and you decide to color Western Australia red first and then color the Northern Territory green, that leads to the exact same state as if you colored the Northern Territory green first and then Western Australia red.
Right. The map looks the same in the end. The history of how we got there is irrelevant.
Exactly. In many other search problems, like finding a path through a maze or playing chess, the order is everything. Moving your knight and then your pawn is a completely different game state than moving your pawn and then your knight.
Right, because in a maze, stepping left then forward puts you in a different spot than forward than left if there are walls involved.
Correct. But in CSPs, we only care about the final assignment. We just need a valid, completed map. This drastically reduces the search tree because we don't have to worry about the sequence of our choices, just the choices themselves. We don't need to explore all permutations of actions, just the combinations of values.
I want to move this out of the abstract for a second. We mentioned the Hubble telescope earlier, but the source material gives a really gritty, real-world example: car assembly.
Yes, the job shop scheduling problem. This is the bread and butter of industrial AI. This is where CSPs, pay the bills. Imagine you were running a massive factory floor. You aren't coloring maps. You are building a sedan.
So let's map this to our X, D, and C. What are our variables here? What's X?
Your variables, your X, are the tasks. Install axles, affix wheels, tighten nuts, inspect brakes, paint chassis. There might be hundreds of them.
And the domains?
The D is time. The domain is the timestamp. When does this task start? Does install axles start at minute 1, minute 10, minute 45?
And the constraints? I assume it's not just don't be the same color.
It gets much more flavorful here. You have different types of constraints mixing together. First, you have precedence constraints. Logic dictates you cannot put the wheel on before the axle is installed.
Unless you want a very strange-looking, non-functional car. Or maybe a hover car.
Even hover cars need structure. So mathematically, that constraint looks like arithmetic. Start time of axle plus the 10 minutes it takes to install the axle must be less than or equal to the start time of wheel.
So it's an inequality, like T-axle plus 10 is less than or equal to T-wheel.
Exactly. But then you also have disjunctive constraints.
Disjunctive meaning or.
Yes. Suppose you have one specialized robot arm that installs axles. It has to do the front axle and the back axle. It can't do them both at the exact same moment. Doesn't matter which one it does first, but they cannot overlap.
So the rule is front axle happens before back axle, or back axle happens before front axle.
Precisely. The CSP has to handle arithmetic, this takes 10 minutes, and logic, this or that, all at the same time. And looking at the car assembly example, you usually have a hard deadline. The whole car must be off the line in 30 minutes. That limits the domain of every variable to the integers 1 through 30.
It seems manageable when we talk about just putting on wheels, but I assume a real factory has thousands of these variables.
Thousands, maybe tens of thousands. And think about the resources. You have constraints like, we only have 5 wrenches, we only have 3 painters.
And if you tried to solve that with a black box search, exploring every possible timeline minute by minute,
You would be waiting until the heat death of the universe. The number of combinations is just staggering. But with CSP techniques, factories solve these schedules every single morning before the first shift starts. They optimize it to save minutes, which saves millions of dollars.
that's incredible. It really shows how identifying the structure, the variables and constraints is the secret sauce. But I want to pause on the domain part. In the map, our domain was red, green, blue. In the car factory, it was minute 1 to minute 30. Those are finite lists. What happens when the options are infinite?
That brings us to the variations in CSPs. What we've been discussing so far are discrete variables with finite domains. You can write them down on a list, but you can have infinite domains.
Like all the integers or strings of text.
Exactly. Imagine that car factory again, but without the 30-minute deadline. The start time for install axles could theoretically be minute 100, minute 10,000, or minute 1 mils and mel.
You can't list every integer. That's impossible.
No. In that case, you need a constraint language. You don't list the pairs of values that work. You deal with the formulas directly. You use algebra within the AI to understand start time A plus duration is less than start time B.
And what about continuous domains, real numbers with decimals?
That is the realm of operations research and linear programming. Think about that Hubble Space Telescope example. Precise timing of observations isn't just minute 1 or minute 2. It might be minute 1.00543.
Right, because stars move smoothly. They don't just jump from minute to minute.
Exactly. The variables are continuous. You need linear equalities and inequalities to solve those. It's a whole different beast solvable in polynomial time if the constraints are linear. But it fits under the same conceptual umbrella. You are still carving away the impossible to find the possible.
Okay, so we have different types of variables. What about different types of constraints? You mentioned the not equal constraint for the map, which relates to variables.
That is a binary constraint. It relates to variables, Western Australia versus Northern Territory. But you can also have unary constraints.
Unary, so that means one.
Yes, a restriction on a single variable.
Hmm.
Let's say the people of South Australia are incredibly picky. They pass a state law that says, we absolutely refuse to be colored green.
Tough crowd. A purely aesthetic rebellion.
Indeed. So you have a rule. South Australia cannot be green. That is a unary constraint. You can usually solve those instantly.
How so?
You just pre-process the problem. You cross green off the list for South Australia before you even start looking at the rest of the map. It effectively shrinks the domain for that variable from red, green, blue to just red, blue.
That seems efficient. Then I assume there are constraints that involve more than 2 variables.
Those are called global constraints. The name is a bit confusing. It doesn't mean it involves every variable in the entire problem, just an arbitrary number of them. It could be 3, it could be 100.
Can you give me a classic example of that?
The most famous one is all diff. All different.
Ah, like in Sudoku.
Exactly. Think about a single row in a Sudoku puzzle.
Mhm.
You have 9 variables, which are the squares. The constraint is that they must all have different values, the digits 1 through 9.
Right, you can't have 2 5s in the same row. That's the whole game.
Now, you could write that as a bunch of binary constraints. You could say square 1 doesn't equal square 2. Square 1 doesn't equal square 3. Square 1 doesn't equal square 4, and so on.
That sounds exhausting.
It creates a mess of lines on your graph. It's much more efficient to just treat it as one big hyperconstraint called all diff square 1 dot square 9.
It's cleaner and probably easier for the computer to process as a single rule, I'd imagine.
Much easier. The inference algorithms can look at that group of 9 and apply special logic to it, which we'll get to in a minute. Another interesting global constraint is at most.
At most.
Imagine you have a staffing problem. You have 4 tasks, A, B, C, and D. You need to assign personnel to them, but you only have 10 staff members total in your department.
Okay.
The constraint is the sum of personnel on tasks A, B, C, and D must be at most 10. It links all 4 variables together. If you put 8 people on task A, you suddenly only have 2 people left to split between B, C, and D. They're all pulling from the same pool.
That feels like a very real-world manager problem. I don't care how you divide them up, but I only have 10 people, so make it work.
Precisely. And then there's one more twist. Sometimes constraints aren't hard rules. Sometimes they're preferences.
Oh, like, I'd prefer not to work the night shift, but I will if I have to.
Exactly. In a university scheduling problem, Professor X must not teach 2 classes at once is a hard constraint. If you violate that, reality breaks. You can't be in 2 places at once. But Professor X prefers teaching in the morning is a preference.
So how does the AI handle that? It's not just true or false anymore, is it?
It turns the CSP into a copy constraint optimization problem. Each assignment has a cost. Assigning the professor to the afternoon might cost 2 unhappiness points. The goal isn't just to find a valid solution, but the one with the lowest cost.
Fascinating. So we've defined the machinery. We have our variables X, our values D, our constraints C. We have the graph. Now we need to talk about how to actually solve these things. You mentioned earlier that we don't just guess. We use inference.
Yes. This is the superpower of CSPs. In a regular search, you just wander around trying paths. In CSPs, we can use constraint propagation. We can reduce the legal values before we even start searching.
This is the pruning you talked about, cutting off dead branches of the tree before we even climb them.
Think of it as local consistency. We treat the variables as nodes in a graph. We enforce consistency locally right here between these 2 neighbors, and that eliminates impossible values. Then that effect propagates to their neighbors and their neighbors.
A ripple effect.
Exactly. Let's talk about the most common algorithm for this. AC3. It stands for Arc Consistency Algorithm number 3.
Catchy name. It sounds like a droid from Star Wars. AC3 shut down all the trash compactors, so how does it work?
It looks at the arcs or links between variables. Let's say we have variable A, that's Western Australia, and variable B, Northern Territory. To make the arc consistent, we check. For every value in A's domain, is there some value in B's domain that allows this to work?
Okay, let's play this out. WA can be red, green, or blue. NT can be red, green, or blue.
Right, so the algorithm picks red for WA and looks at NT. It asks, if WA is red, can NT be something?
Yes, NT can be green or blue.
Great. So red is safe for WA. Then it checks green for WA. Can NT be something?
Yes, red or blue.
So green is safe. It checks blue. Also safe. So initially that arc is consistent. Nothing changes. But imagine we had that unary constraint earlier, the one where South Australians outlawed the color green.
Right, so South Australia's domain is just red-blue.
Now let's look at the arc between Western Australia and South Australia. WA has red, green, blue. SA has red, blue.
Okay.
The algorithm checks green for Western Australia. It asks, if WA is green, is there a valid color for SA?
Yes. SA can be red or blue. Both of those are different from green.
Correct. But now imagine WA only had green left for some reason. Or let's make it harder. Imagine WA is red-blue and SA is just red.
Okay, so SA is forced to be red. There's no other choice.
I check the arc from WA to SA. We check red for WA. If WA is red, can SA be anything?
No. SA has to be red, so they would be the same, which isn't allowed.
Exactly. So red in WA's domain has no support in SA's domain. So AC3 deletes red from WA.
Pruned. Gone.
And here is the cascade. If I delete red from Western Australia, that might screw things up for Western Australia's other neighbor, the Northern Territory.
Because maybe the Northern Territory was counting on WA being red to make its own logic work out.
Exactly. If I shrink a domain, I have to recheck all the neighbors. So AC3 keeps a queue of arcs to check. Every time a domain shrinks, we add the neighbors back into the queue. We keep doing this until the queue is empty.
And at that point, what happens?
At that point, the network is arc consistent. Sometimes that solves the whole problem. If every variable is left with just one option, you're done. You didn't even have to search. You just let the logic ripple through.
That sounds magical, but I'm guessing it doesn't always work out that perfectly.
No, unfortunately not. Sometimes you're on AC3 and you are left with multiple options for each variable. Or, in tricky cases, it might look consistent locally, but there is no global solution.
The source material mentions the map coloring with only 2 colors as an example of this failure.
Right. Imagine trying to color Australia with only red and blue. We know it's impossible because WA, NT, and SA all touch each other in a triangle. You need 3 colors for a triangle.
It's the Three's Company problem.
But arc consistency only looks at pairs. It only looks at 2 at a time.
So WA looks at NT and says, I'm red, you're blue, we're good.
And NT looks at SA and says, I'm blue, you're red, we're good.
And SA looks back at WA and says, I'm red, you're blue, we're good.
Locally, every pair is fine. The arc consistency check passes, but globally, the triangle fails. AC3 isn't smart enough to see the triangle's structure. It has tunnel vision.
So we need stronger inference. We need to look at more than just pairs of things.
That leads us to path consistency, or 3 consistency.
Yeah.
Instead of looking at pairs, we look at triples of variables. We ask, if I choose X and Y, is there a valid Z?
And that would catch the Australia triangle problem.
Yes. It would see that for the pair WA red, SA blue, there is no valid option for NT, which touches both. So it would prune the possibilities for WA and SA until nothing is left, telling us immediately, impossible.
And you can generalize this, right? K consistency.
Exactly. 1 consistency is node consistency. 2 consistency is arc. 3 is path. You can go up to K consistency. If a problem has n variables and you enforce n consistency, you're guaranteed to find a solution without ever having to backtrack.
That sounds like the magic bullet. Why don't we just always use n consistency? Why mess around with AC3 at all?
Well, because there is no free lunch in computer science. Calculating n consistency takes exponential time and space. To enforce n consistency, you basically have to solve the problem in your head to prove it's consistent. It becomes just as hard as solving the problem the old-fashioned way.
So it's a trade-off, a massive one.
In practice, we usually stick to arc consistency, or AC3, because it offers the best bang for your buck. It's fast, and it does a lot of pruning, even if it doesn't catch everything.
I want to apply this to something everyone listening has probably done. Sudoku. The source material claims Sudoku is basically just a CSP.
It is a textbook CSP, 81 variables, which are the squares. The domain is digits 1 through 9. And you have 27 all-diff constraints, the rows, the columns, and the 3x3 boxes.
And when we play Sudoku and we say, oh, the square has to be a 4 because there is a 4 in this row and a 4 in this column, that's just arc consistency, isn't it?
That is exactly what you are doing. You are manually running the AC3 algorithm in your head. You are eliminating values from the domain based on binary constraints. In fact, AC3 can solve almost all easy and medium Sudoku puzzles instantly.
But not the hard ones, right?
No. For the hard ones, AC3 runs out of steam. It leaves you with multiple options for the squares. That is where human players start using advanced strategies. You might know the term naked triples.
I have heard of it. It sounds a bit scandalous for a puzzle, but explaining it makes me feel like a genius.
It's purely logical. It essentially says, in this row, there are 3 squares that can only contain the numbers 1, 3, or 8. We don't know which is which. Maybe the first one is 1, maybe it's 8, but we know those 3 numbers are locked into those 3 squares.
Right, because they have nowhere else to go in that row.
Exactly. So even though we haven't solved those squares yet, we can delete 1, 3, and 8 from the domains of every other square in that row.
That is brilliant.
And mathematically, that is just enforcing consistency on the global all-diff constraint. It's a higher order inference. It shows that what puzzle aficionados call strategies are really just deeper levels of CSP constraint propagation.
So we've used inference, we've run AC3, we've pruned the domains, we've done the naked triples, but let's say we still haven't solved it. We still have variables with multiple options. What happens now?
Now we have to search. We have to guess.
Back to the black box.
Not quite. We are still smarter than that.
Right.
We use backtracking search. It's a depth-first search. We pick a variable, assign it a value, and move to the next. If we hit a dead end of violation, we backtrack, we undo the last step, and try a different value.
But here's where we can be clever. We don't just pick variables randomly. We have heuristics. We have strategies for how to guess.
Right. We have 2 main questions to answer to be smart about this. Which variable do I pick next, and which value do I give it?
Let's start with the variable. I'm looking at my map. I have Western Australia, Tasmania, Victoria. Who do I color first?
The best strategy is usually the minimum remaining values heuristic, or MRV, also known as fail first.
Fail first? That sounds pessimistic. Why would I want to fail?
It is efficiently pessimistic. You pick the variable with the fewest legal moves left.
So if Tasmania has 3 colors available, but South Australia only has 1 color available.
You pick South Australia immediately, no question.
Yeah.
Because if South Australia only has 1 option, it is fragile. It is a bottleneck. If you leave it for later, by the time you get there, that 1 option might be gone, and you'll have to backtrack all the way.
Ah, I see.
If you are going to fail, you want to fail now, at the top of the search tree, not 3 hours later. You want to force the issue. If a variable is going to cause a problem, put it in the spotlight immediately.
That makes a lot of sense. Do the hard work while you have resources. What if there is a tie? Say everyone has 3 colors left.
Then we use the degree heuristic. Pick the variable involved in the most constraints. In Australia, that's South Australia again, it touches 5 other regions.
Right, because coloring it will have the biggest impact on the rest of the board.
It reduces the branching factor for the future variables. It constrains the rest of the problem the most effectively. It says, I am the most connected node. Deal with me first so everyone else knows where they stand.
Okay, so we've picked the variable, say, South Australia. We are following the fail first rule. Now we have to give it a color. Red, green, or blue. How do we choose the value?
Here, we flip the logic completely. We use the least constraining value heuristic. We try to fail last.
Wait, hold on. For variables, we want to fail first. For values, we want to fail last. That sounds totally contradictory.
It does, doesn't it?
Yeah.
But it's a beautiful paradox. Think about it. For variables, we want to find the dead ends early to prune the tree. But once we commit to a variable, we want to pick the value that is most likely to succeed. We only need one solution.
So we want to be nice. We want to play well with others.
Exactly. When we pick a color for South Australia, we should pick the one that leaves the most options open for its neighbors. We want to be accommodating.
So if choosing red leaves my neighbor Western Australia with 2 options, but choosing green leaves Western Australia with 0 options.
You choose red, obviously. You want to keep the possibilities alive for as long as possible.
So the strategy is pick the variable that is most likely to crash the party, which is fail first, but give it the value that is least likely to cause a fight, which is fail last.
That is the perfect summary. It's like seating the troublemaker at the dinner table first, but giving them their favorite meal so they stay quiet.
Now, searching isn't enough. We have to combine search with inference. We don't just guess and close our eyes.
Right. This is where we get into techniques like forward checking. When you assign Western Australia equals red, you don't just move on. You immediately look at its neighbors. You cross red off their lists.
And if one of those neighbors runs out of colors because of that,
You backtrack immediately. You don't wait to actually visit that neighbor. You see the train wreck coming and you stop.
but the source material says forward checking isn't enough. It mentions something called MNC, maintaining arc consistency.
Forward checking only looks one step ahead. It checks the immediate neighbors. MAC is the nuclear option. When you assign a value, it runs the full AC3 algorithm recursively.
Whoa.
It checks the neighbors, then checks their neighbors and their neighbors. It propagates the implications of your guess as far as possible through the entire graph.
So MSC is doing a lot more work at each step. That sounds like a lot of heavy lifting.
It is, but it saves time in the long run because it prevents you from going down deep, doomed paths. For hard problems, MSC is almost always better. It's like playing chess and thinking 10 moves ahead versus just one.
Okay, so we are searching, we are predicting, we are pruning. But sometimes, despite all our cleverness, we still get stuck. We hit a wall, we have to backtrack. And the source material has a great example of how dumb standard backtracking can be.
The dumb backtracking versus intelligent backtracking debate.
Yeah. Let's look at chronological backtracking. Let's say we are coloring Australia. We color WA, NT, Queensland, NSW, Victoria, and then we get to South Australia.
The troublemaker.
And we realize, oops, no colors left. South Australia touches everyone, and we used all the colors on the neighbors. We are completely stuck.
In simple chronological backtracking, the algorithm just backs up to the most recent step, which geographically was probably Tasmania.
Tasmania, the
Yeah.
island that touches nobody.
Right. So the algorithm says, oh, South Australia failed. Let me change Tasmania. It changes Tasmania from red to green and tries South Australia again.
Which changes absolutely nothing. South Australia is still stuck because Tasmania has 0 effect on it.
Nothing changes. So it changes Tasmania to blue. Still stuck.
Yeah.
It runs through every option for Tasmania before realizing, wait, Tasmania isn't the problem? Then it backs up to Victoria.
That is painful to even think about. It's like losing your keys in the kitchen, but looking for them in the bedroom because the light is better there.
It is. So we use intelligent backtracking, specifically something called backjumping.
How does that work? How does it know where to jump?
We keep track of conflict sets. When South Australia fails, the algorithm doesn't just cry, it asks, why? Who did this to me?
The blame game. I like it.
Exactly. It looks at the constraints. It sees that its domain was emptied by WA, NT, Q, NSW, and V. Notice that Tasmania is not on that list.
So we jump over Tasmania.
We jump straight back to the most recent variable in the conflict set, which would be Victoria. We skip the irrelevant decisions entirely.
That is so much smarter.
And we can go deeper with conflict-directed backjumping. If backing up to Victoria doesn't fix it, because Victoria itself was forced into a corner by earlier choices, we merged the conflict sets. Victoria says, hey, don't look at me. I failed because of Queensland and NSW. So South Australia inherits those problems. We can jump back multiple levels to the true source of the conflict.
It's like a root cause analysis happening in real time.
And we can even learn from our mistakes. This is called constraint learning. When we find a combination that breaks the puzzle, say WA is red and NT is green leads to failure, we record that as a new constraint, a no good.
A no good. I like that term. It sounds like something a cowboy would say. That's a no good varmint.
Exactly. We write it down so we never explore that specific dead-end subtree again. We're essentially modifying the problem map as we solve it, adding warning signs to the cliffs we've already fallen off.
I love that. It's the algorithm learning from experience.
Precisely.
Now, everything we've talked about so far involves building a solution from scratch. Empty map, start coloring. But there is a completely different way to approach this, isn't there? The local search approach.
Yes. This is the repair approach. Imagine you just splash colors onto the map randomly. Or you throw 8 queens onto a chessboard anywhere.
It's going to be a mess. Constraints violated everywhere, queens attacking queens, red touching red.
A total mess. But instead of starting over, you try to fix it. This is the min conflicts heuristic.
How does it work?
You pick a variable that is currently breaking a rule, say a queen that is currently attacking another queen. You look at all the possible spots in its column, and you move it to the spot where it attacks the fewest other queens. Minimum conflicts.
It sounds too simple. Just greedy fixing. I'll move here because it looks safer.
It sounds incredibly simple, but the results are shocking. The source material mentions the million queens problem.
Yeah, putting mills and thousand queens on a million by million board so none attack each other, that just sounds impossible.
If you tried to do that with the backtracking methods we just discussed, building it one by one, it would take years, maybe centuries. The search tree is just too deep.
But with min conflicts.
It solves it in an average of 50 steps.
Wait, 50 steps? 50. For a million queens.
Approximately 50 steps after the initial random assignment. It is shockingly effective. It turns out that for many CSPs, solutions are densely distributed. You just need to wiggle things around a bit to click them into place.
And this has real applications, right? It's not just for chess puzzles.
Absolutely. The Hubble Space Telescope scheduling we mentioned. In the early days, NASA used to struggle to schedule a week's worth of observations. It took 3 weeks of computer time to schedule 1 week of viewing.
3 weeks to schedule 1 week. That's not sustainable. You're losing time. The universe is expanding while you're buffering.
Exactly. They switched to a min conflicts-based local search. It cut the time down to 10 minutes.
From 3 weeks to 10 minutes. That is the power of choosing the right algorithm.
It is. But local search has its risks. You can get stuck on a plateau.
A plateau. I'm picturing a hiker.
Imagine the landscape of the problem. You are trying to climb down into a valley of 0 conflicts. Sometimes you hit a flat area where every move you make results in the same number of conflicts. You don't know which way is down.
You're just wandering in the dark on a flat soccer field.
Exactly. So we use tricks like taboo search. We keep a list of the last few states we visited and say, don't go back there. It forces the algorithm to explore new directions, preventing it from walking in circles.
Or constraint weighting.
Yes. If a particular constraint is being violated over and over, we give it a weight. We make it heavy. We tell the algorithm this specific rule is really important. Prioritize fixing it. It changes the landscape, creating a slope where there was a plateau, guiding the search downhill.
So we have these amazing tools, inference, backtracking, local search. But the source material makes one final, really deep point. It's about the structure of the problem itself.
Yes, this is the divide and conquer strategy.
Going back to Australia, Tasmania.
Tasmania is an independent subproblem. It is not connected to the mainland. We can solve Tasmania red, green, or blue completely independently of the mainland.
And mathematically, breaking a problem into independent chunks is a total game changer, isn't it?
It turns an exponential problem into a linear one. If you can chop a massive problem into huge independent pieces, you win. O of 2 to the n becomes O of n times 2 to the k.
But most problems aren't that clean. Everything is connected.
True. But sometimes they are connected in a specific way, like a tree.
The tree structure, you mean no loops.
Exactly. If your constraint graph has no loops, node A connects to B, B connects to C, but C never circles back to A, you can solve it in linear time. Guaranteed. No backtracking needed.
How?
You use a topological sort, you order the variables from parent to child, you enforce directed arc consistency. Then you just walk down the tree picking values. It works every time.
Okay, but Australia has loops. WANTSA forms a triangle loop. Most real problems, like the factory floor, have loops all over the place.
So the trick is, can we turn a graph into a tree?
How do we do that? It sounds like we're breaking physics.
Two ways. First, the cycle cut set. You identify the troublemakers, the variables that create the loops. In Australia, if you remove South Australia, the rest of the map becomes a tree.
Because South Australia touches almost everyone, it's the hub.
Right. So we cut it out. We fix a value for South Australia, say SA is blue. We remove it from the graph and update the neighbor's domains. Now we solve the remaining tree.
And if that doesn't lead to a solution,
We try SA equals red, then SA equals green. We solve the tree for each possible value of the cut set variables.
that's clever. It isolates the complexity into just that one variable.
The second method is tree decomposition. We group variables into subproblems, little clusters that connect to each other like a tree. If the tree width, the size of these clusters, is small, the problem is efficient to solve.
So it's all about finding the hidden structure, the skeleton within the mess.
Exactly. If you can find the tree hidden inside the graph, you can solve it.
We have covered a lot of ground today. I mean, from coloring books to space telescopes. We moved from the black box of search to the factored world of variables, values, and constraints.
We looked at the machinery, types of constraints, the power of inference in AC3,
We looked at search, fail first, fail last, backtracking and backjumping.
and we looked at local search, fixing the broken solution with min conflicts, and the importance of structure, like trees and cut sets.
Before we wrap up, there's one little detail in the source material I found interesting: value symmetry.
Ah, yes. The idea that if you have a solution, WA is red, NT is green, SA is blue, you actually have 6 solutions just by swapping the color names. Red becomes blue, blue becomes green, etc.
Which is a waste of search time, fighting the same solution 6 times.
So we introduce symmetry breaking constraints. We add a rule like Western Australia must be alphabetically before Northern Territory. It forces the computer to find just one version of the solution, slashing the search space by a factor of n factorial.
Just another cheat code in the arsenal. So, leave us with a final thought. We've unpacked all this logic. What's the big takeaway for the listener?
I think the most provocative idea here is about where the hard problems actually live. Research shows that most random CSPs are either trivially easy, inference solves them instantly, or obviously impossible.
Really?
Yes. The truly hard problems, the ones that take time, that require complex backtracking, they exist in a very narrow phase transition, just like water freezing into ice. They sit right on the edge of solvability.
That's poetic.
It is. The world is full of constraints, and the problems that challenge us the most are the ones balanced perfectly on that knife edge. So when you face a complex problem in your life, ask yourself, are you trying to search a black box? Or can you uncover the constraints, find the variables, and let the logic prune the path for you?
That's it for this deep dive. Thanks for listening, and keep finding those constraints.